All right, in this video, we will be going over section 5.4. Section 5.4 is about trigonometric integrals. And basically, we are going to learn how to integrate various types of trigonometric functions. And you are going to learn certain techniques to deal with trigonometric integrals. All right, I want to start with a small introduction. Usually, we have seen that the use substitution has been a very powerful tool in integrating. Okay, so the key to the use substitution is that you need to view your integrand. Integrand is the function that you are integrating. Okay, if you have an integral of this form, g of x dx, then this is the integrand. Okay, if you can view your integrand in this form, somehow you can rewrite your integrand in this form, you can use the use substitution to solve that integral. Okay, so here we are going to deal with trigonometric integrals, and again the key is to write our integrand in this form. Okay, to write your integrand in that form, we are using certain techniques. Basically, mainly we are using Pythagorean identities to write our integrand in this form. Okay. All right. For that, I want to first go over some Pythagorean identities that you have learned in your pre-calculus class. Here is the theorem, the first theorem that I want to go over, theorem 5.15, Pythagorean identities. For all values of x at which the following equations are defined. We have first part, sine squared x plus cosine squared x is equal to 1. Tan squared x plus 1 is equal to secant squared x. 1 plus cotangent squared x is equal to cosecant squared x. Okay, these are very preliminary identities that you have seen in your pre-calculus class. All right, let's move on. And then we have this double angle identity theorem, theorem 5.16, double angle identities. For all real numbers x, we have these double angle formulas. Sine squared x is equal to 1/2 times 1 minus cosine 2x, and cosine squared x is equal to 1/2 times 1 plus cosine 2x. All right, let's move on. Here is the first integral formula that we have, theorem 5.17, integrals of secant and cosecant functions. Okay, so the integration of the first part, the integration of secant x is going to be ln secant x plus tan x plus a constant. Okay, how do you prove that this formula is true? All what you need to do is show that this is an antiderivative of your integrand. Your integrand is secant x. Okay, that will prove that the indefinite integral of secant x is exactly this function, function plus a constant. Okay, take the derivative of this part and show that you get secant x. That's it. And the next integral formula is the integral cosecant x dx is equal to minus ln cosecant x plus cotangent x, absolute value of course, plus a constant. Okay, here also make sure that you have the absolute value. Okay, all right, again to show that this formula is true, you need to show that this is an antiderivative of your integrand, which is cosecant x. Take the derivative of this piece and show that you get cosecant x. That's a so straightforward calculation, so I'm not going to go over the proof. Let's move on. All right, here is where we are going to start our trigonometric integrals. Okay, we are going to discuss various techniques in dealing with trigonometric integrals. This chart, this table summarizes some techniques that we can use for trigonometric integrals. Okay, so here's the first type that I want to talk about. All right, if you have an integral of this form, integral sine nx, the power is n. Okay, sine nx dx with n odd. First, you need to rewrite this integral of this form. You need to write sine x dx at last, and then the remaining thing should be an expression in cosine x, And in that case, your substitution is going to be u is equal to cosine x. And the next type is if you have an trigonometric function of this form, sine mx all right, if you have an integral of this form, integration sine nx dx, n is the power, okay, with n is odd, then you need to rewrite this integration in this form. You need to write sine x dx at last, and the remaining thing you need to write in terms of cosine x. And in that case, your substitution is going to be u is equal to cosine x, and clearly du is going to be minus sine x dx. And then the next type is integrations of this form. Okay, if you have an integral of this form, sine mx times cosine nx with n is odd, then first you need to rewrite this integration in this form. Okay, cosine x dx at last, and then you write the remaining thing in terms of sine x. In that case, your substitution is going to be u is equal to sine x. And then if you have an have a trigonometric function of this form, sine mx cosine nx with m is odd, then you need to write your rewrite your original integral in this form. Okay, sine x dx at last, and then you write the remaining thing in terms of cosine x. Your substitution is going to be u is equal to cosine x. And then trigonometric functions of this form, secant mx tan nx with m is even, then you need to write this original integral of this form, secant squared x dx at last, and you need to write the remaining thing in terms of tan x. In that case, your substitution is going to be u is equal to tan x. And this is the next case. If you have secant mx tan nx with n is odd this time, then you need to write your original integration in this form, secant x tan x dx at last, and then the remaining thing in terms of secant x. Your substitution is going to be u is equal to secant x. I have added two additional formulas here. If you have an integral of this form, integration of cosecant mx cotangent nx with m is even, then you need to write your integral, original integral in this form, cosecant squared x dx at last, and then you need to write an expression remaining thing as a function of cotangent x. Okay, in terms of cotangent x, and in that case your substitution is going to be u is equal to cotangent x. Okay, and the next type is if you have a trigonometric function of this form, cosecant mx times cotangent nx with n is odd, then you need to rewrite this original integral in this form. You need to write cosecant x cotangent x dx at last, and then you write the remaining thing in terms of cosecant x. And in that case, your substitution is going to be u is equal to cosecant x. All right, now let's work on an example to understand what's going on here. Okay, so the first example, I want to start with this first part. Let's read the example first, by the way. Use algebra and u substitution to find each of the following integrals. Let's work on this one. How do you find this integral? Well, you go with this table. Okay, let's see what the table suggests us. Which substitution can we use to solve this integral? Well, if you look at these substitutions, you need to find the correct form here. Okay, here we have the power of sine is odd, power of cosine is even. Okay, so looks like this is the form that we need to go with. Okay, because m is odd. M is odd means the power of sine is odd. So that's what you have here. I don't care about the power of the cosine x. Okay, so I'm trying to go with this substitution. U is equal to cosine x. Before that, I need to write my original integral in this form. Okay, let's try to write our original integral in that form. So this is my original integral, integration sine cube x cosine 4x dx. I need to write this this way, integral sine squared x cosine 4x sine x dx. That's the form I want here. If you go to this third one here, I need to write sine x dx at last. But here I need to write everything as an expression of cosine x. Okay, you need to have an expression in cosine x here. How do you get an expression in cosine x here? Well, all what you need to do is you need to use trigonometric identities. We know that sine squared x is 1 minus cosine squared x. That will give us the form that we are interested in. 1 minus cosine squared x times cosine 4x sine x dx. Now all you need to do is go with the substitution. We know that in that case substitution is, our substitution is going to be u is equal to cosine x. Let's go with that substitution. U is equal to cosine x. Of course your du is going to be minus sine x dx. Now if you divide both sides by minus 1, then you get minus du is equal to sine x dx. So I found my sine x dx because I need to plug in that here. Okay, I have sine x dx here, so that is going to be minus du. Now let's do the substitution. If I do the substitution, then my integration becomes 1 minus u squared, cosine x is u, and then u to the power 4 times sine x dx. Here sine x dx, which is minus du. So I can pull that minus sign out here. You get du. Okay, so your integral, your integration is going to be this simple integral, which you know how to solve. Okay, so let's find this integral. This is going to be minus times u to the power 4 minus u to the power 6 du, and then of course you can integrate this. This is going to be minus times u to the power 5 divided by 5 minus u to the power 7 divided by 7 plus a constant, plus some constant. Okay, now you are not done yet because you need to back substitute for u. Your u is cosine x. That's your substitution. So you back substitute that here. You get minus cosine 5x divided by 5 plus cosine 7x divided by 7. I'm sorry, I'm writing on the table, plus c. Okay, that gives you the answer. Of course, you can verify these answers if you can differentiate this part and show that you get this one, but that will involve with some sort of a trigonometric calculation. All right, so that completes that part. Let's move on to the next part. In the next part, as you can see, the power of cotangent is odd and the power of cosecant x is even. Okay, you have the product of cosecant and cotangent. So which situation are we in if you look at the table here? Well, I'll go to the other side. Here is the table. Which situation are we in when the power of cosecant is even and power of cotangent is odd? We are in this situation, right? Because the power of cotangent is odd. Okay, and in fact, in this case, we can use even this case because the m is even. M means the power of cosecant. Power of cosecant in this case is even. You can use either of these substitution. Either you can use u is equal to cotangent x or u is equal to cosecant x in this case, because we have the powers that we need in both cases. All right, let's go with one of them. I'll go with u is equal to cotangent x. Remember, before I use this substitution, I need to write my original integration in this form. Okay, some expression in cotangent x times cosecant squared x dx. Let me do that. So my integral becomes part B. Okay, my integral becomes cosecant 4x cotangent power 3x dx. That becomes integration. Oh, this is cosecant, pardon me, not cosine. Cosecant 2x cotangent 3x cosecant squared x dx. Okay, that way I have cosecant squared x dx at last. That's what I want. Okay, I wanted cosecant squared x dx at last. Okay, and then I need to get the remaining thing in terms of cotangent x. How do you get the remaining thing in terms of cotangent x? Well, it's going to be using some trigonometric identities. This is going to be cosecant squared x is actually 1 plus cotangent squared x times cotangent cube x cosecant squared x dx. Now I'm ready to go with my substitution. My substitution is going to be u is equal to cotangent x. Remember, my substitution is going to be u is equal to cotangent x. If I do this, I get my du is equal to minus cosecant squared x dx. Okay, that's my du. Now, from this one, you can easily see that cosecant squared x dx is equal to minus du. Okay, minus du is equal to cosecant squared x dx. All right. Now I'm ready to go with the substitution. I will plug in my substitution here. Then my integration becomes integration 1 plus cotangent squared, that is 1 plus u squared, times cotangent cube x, that is u cube, times cosecant squared x times dx, which is minus du. I can pull that minus sign out over here, and I should have du. Now, this is an integration that you know how to solve. Okay, let's go ahead and solve this one. If you solve this, I'll write it over here maybe. You have minus sign in front. Then you have u to the power 4 divided by 4. I'm integrating the function straight away. Okay, u to the power 6 divided by 6 plus a constant. Okay, I multiplied this by this, and then this term by this term, and then I integrated those two terms. You get u to the power 4 divided by 4 and u to the power 6 divided by 6. Okay, we are not done yet. We need to back substitute for u. If you do the back substitution, you will get minus cotangent x, cotangent 4x divided by 4 minus cotangent 6 divided by 6 plus c. I'm just substituting u is equal to cotangent x. Okay, that's it. So this is your final answer. All right, that completes that part. Let's move on to the next part, part C. How do you integrate this expression? How do you integrate secant cube x times tan cube x? Well, let's go to the table and find the correct substitution. Okay. So here, as you can see, both the odd numbers, both powers are odd, right? So let's go ahead and find the correct substitution from the table. See, here is the substitution that we need to go with. Okay, when n is odd, you have a product of secant and tan with both m and n are odd. And if n is odd, you can go with this substitution. U is equal to secant x. Okay. Before you go with this substitution, you need to write your original integral of this form. Okay, secant x tan x dx at last, and the remaining thing in terms of secant x. Let's do that. All right, here, this is the integral I have. Secant cube x tan cube x dx. I'm rewriting that integral. Maybe I will go to the next line. Secant squared x times tan squared x secant x tan x dx. Okay, I rewrote my original integral. To get the desired form, I need to have secant x tan x at the end. Okay, of course, if you simplify this expression, you get this integrand back. All right, now I'm ready to go with my substitution. What is my substitution? According to the table, I am going to have to use u is equal to secant x. Then you get du is equal to secant x tan x dx. Now I'm ready to go with my substitution. Okay, my integration is going to be equal to, before I go to my substitution, remember, you need to write this remaining piece. You need to write this remaining piece in terms of secant. Can we write this whole thing in terms of secant? Yes, all what you need to do is you need to replace this tan x with an expression in terms of secant x. Can we do that? Yes, we know that tan squared x is, your tan squared x is secant squared x minus 1. So I can put secant squared x minus 1 here. Actually, I will write that first before I write this one. All right, remember, first you need to write this whole thing in terms of secant x. So that's what I did here. Secant squared x times tan squared x is nothing but secant squared x minus 1. And I have this desired piece at last. Okay, now I'm ready to go with the substitution. This is the substitution that we took. Let's write our integral using the substitution. Integration secant squared x, which is u squared, times u squared minus 1. Secant x dx tan x is just du. The integral of this one would be u to the power 4 divided by 4 minus u to the power 3 divided by 3 plus a constant. Okay, to get the final answer, you back substitute for u. Your u was secant x. You have secant 4x divided by 4 minus secant cube x divided by 3 plus c. That's your final answer. Okay. All right, that completes that example. Let's move on. Next, I want to work on this particular example. Again, we need to use double angle identities to find each of the following integrals. Okay, so this is a new example, of course, an application of double angle formula. All right, so let's work on the first part. How do we solve the integration cosine 6x dx? Here, what we do is we use double angle formula to simplify this expression algebraically first. Okay, we are going to simplify cosine 6x algebraically before we integrate that. Okay, so cosine, let's do some algebra here. Cosine 6x is equal to, what I'm going to do is I'm going to write cosine squared x to the power 3. If I write that way, I know a double angle formula for cosine squared x by the previous theorem that we discussed. Here is the formula. Cosine squared x is 1 plus cosine 2x times 1/2. So let's do that here. Let's plug that in here. You get 1 plus cosine 2x divided by 2 to the power 3. Okay. Next, I'm going to FOIL this one. This is power 3, right? I write 3 factors of this, and then I FOIL that one. If I FOIL that one, here is what you're going to get. Okay, please check these calculations. You should get these answers. Get this expression if you simplify it correctly. 1/8 plus 3/8 times cosine 2x plus 3/8 times cosine squared 2x plus 1/8 times cosine cube 2x. Okay, that's what you get if you FOIL this expression, or if you expand this expression. Okay, now what I'm going to do is, again, I'm going to use the double angle formula for this one. Okay, if I use the double angle formula here again, let's see what we get. This is going to be equal to 1/8 plus 3/8 times cosine 2x plus 3/8 times 1 plus cosine 4x divided by 2. 1 plus cosine 4x divided by 2 plus 1/8 times, I will leave this cosine cube 2x as it is. Even though this expression is a longer expression than this one, in terms of integration, it is easy to integrate this one than this one. Okay. All right. Now let's try to integrate this function. That means we are going to integrate this long function. Okay. All right. Let's start the integration. Integration cosine 6x dx is equal to integration 1/8 dx plus integration. Of course, I can work this constant out if I want, but let me write it like that for the time being. Cosine 2x dx plus integration 3/8 1 plus cosine 4x divided by 2 dx. Finally, I have integration 1/8 cosine cube 2x dx. Okay. Now I can deal with all of these integrations. We know how to deal with these integrations. We know how to solve these integrals. Okay. So let's go ahead and solve those, and then we will spare this for the next step. All right. Right. I copied the previous integral to a new page. Now, as you can see, you can integrate all of these three. You can find these first three integrals. The integration of this one is, of course, x/8, and then the integration of this one, you can pull this 3/8 out, and the integration of cosine 2x is sine 2x divided by 2. That's clear. And then here you can distribute this integral, since you have summation here. And then if you integrate, you will get the first term is going to be 3/16 times x. And then the integration of the next term will be 3/16 times the integration of cosine 4x, which is sine 4x divided by 4. So only a remaining piece of the puzzle is to find this integral. Okay. Now let's deal with that integral as a separate issue. So we need this integral cosine cube 2x dx. What I'm going to do is I'm going to rewrite this integral as cosine squared 2x cosine 2x dx. Then I'm going to write this whole thing in terms of sine. I'm going to use a similar strategy that we used in the first example. Not in the first example, the first substitution in the table. All right, here we have 1 minus sine squared 2x. We know that cosine squared 2x is 1 minus sine squared 2x. You have cosine 2x dx. Now let's use the substitution. U is equal to sine 2x. Then you get du is equal to minus, cosine 2x times 2. I'll put that 2 in front here. Now we can go with this substitution. Okay, so if I go with this substitution, I have this integral cosine cube 2x dx should be equal to integration 1 minus u squared. Notice that sine 2x is u, so you should have 1 minus u squared times cosine 2x dx, cosine 2x dx, oh pardon me, here you should have dx, okay, dx. Cosine 2 dx is du divided by 2, or 1/2 times du. This is going to be, I'll pull 1/2 out, then you get u minus u to the power 3 over 3. Plus a constant. So if you back substitute for u, you get 1/2 times sine 2x minus sine cube 2x divided by 3 plus a constant. That's what you get. Now all you have to do is you have to go ahead and plug in this expression for this one. Okay. I'll go ahead and plug in this quantity for this integral. We calculated this integral, and this integral is equal to this expression right here. Okay, so if I do that, I get 1/8 times sine 2x minus sine cube 2x divided by 3 plus a constant. That's my final answer. All right, let's go to the next part. Next part is part B. Let me copy this to a new page. All right, how do we solve this particular integral? Okay, here again, we are going to use some algebraic techniques. What I'm going to do is, I'm going to reduce the power. I have sine squared x, cosine squared x, dx. This is equal to, I'm going to write sine squared using double angle formula. That's going to be 1 minus cosine 2x divided by 2. Cosine squared x is 1 plus cosine 2x divided by 2. That's what you get if you use the double angle formula. Now, I'm going to pull out a 1/4 because you have 2 here, that will become 4. You can pull out 1/4. Then this is going to be 1 minus cosine squared 2x. That's because this is factors of difference of 2 squares. Okay, 1 minus cosine x, 1 plus cosine x. That is 1 minus cosine squared 2x. All right, what are we going to do next? Of course, if you want, this can be written as 1/4 times 1 minus cosine squared x is cosine squared 2x is sine squared 2x. We know that from the Pythagorean identity. Now what you can do is 1/4. Again, you can reduce the power here. Note that I'm forgetting my integral sign here. Integration dx. Integration sine squared 2x is 1 minus, by double angle formula, 1 minus cosine 4x divided by 2 dx. Okay, as you can see, we started with the power 2 expression. Now somehow we rewrote our original integration so that we have power 1 expressions everywhere. See, here we have cosine 4x, power is 1. So we can deal with those type of integrations, okay, easily. This is 1/4 times, of course, I can write 1/8 by pulling out that 2 in the bottom. Then you get integration 1 dx minus integration cosine 4x dx. This is going to be 1/8 times x. Integration 1 dx is x. The integration of this function. What is the integration of this? That's going to be sine 4x divided by 4. Small u substitution will give you the answer. Okay, you use u is equal to 4x, then you will see that the integration is going to be sine 4x divided by 4. if you want me to write, use u substitution here. U is equal to 4x. Will give you this answer. All right, plus a constant. Don't forget your constant. Because these are indefinite integrals, you need to have a constant. Okay. All right, that completes that example. Let's move on. The next example that I want to go over is this example. All right, let's work on this integral. This is a special integral actually. When you learn integration, you will see that in any textbook you will see this integral. This is a very special integral. To solve this integral, we need to solve this integral. To solve this integral, we use integration by parts. That's a special technique that we can use here. So how do we use integration by parts here? What I'm going to do is I'm going to identify my original given expression as u dv. Remember, integration u dv is equal to uv minus integration v du. So I need to identify my u and dv. Okay, I'm going to rewrite my original integral secant cube x dx this way. Secant x times secant squared x dx. Okay, now I'm going to make my identification. I'm going to identify this this function as my u and this as my dv. Okay, I'm going to take u is equal to secant x. That will give me du is equal to secant x tan x dx, and I'm going to identify my dv to be secant squared x dx. That will give me, by anti-differentiating, v is equal to tan x. If you integrate both sides, you get v is equal to tan x. All right, now I have everything to go with this integration by parts formula. This is equal to uv, that is secant x times tan x minus integration v du. My v is tan x du. My du is secant x tan x dx. Secant x tan x means this becomes tan squared, right? Tan squared x secant x dx. All right, next what I'm going to do is I'm going to write this tan squared as secant squared minus 1 for a reason. Actually, before that, let me give this integral a symbol. I'll take this integral as I. That's what I need to find at the end of the day. Okay, so I am giving a label for a reason. You will see why I'm giving that label. Okay, all right, so this is simply I. That means this is I. This is I. So now what I'm going to do is I'm going to write this as secant squared x minus 1, because tan squared x is secant squared x is x minus 1. This is equal to secant x tan x minus integration secant squared x minus 1 times secant x dx. I'll separate this out. Now something very interesting happening here. Okay, if you simplify this, you get secant x tan x minus secant cube x dx plus secant x dx. Now, as you can see, this is I. This is the same thing as I. That's the original integral with a minus sign in front. So I can plug in I here. You put I here, and then you move that I to the other side, because it's minus I, right? You have minus I here. You can move this minus I to the other side. If you do that, you get 2i is equal to, because I plus I is 2i, is equal to, let me write it in red, 2i is equal to secant x tan x plus the last integral, secant x dx. Okay, I moved this term to the other side. This is I. If I move that to the other side, it becomes plus I. So we have 2i in the left hand side. Okay, now what? Now we know how to integrate this one. We learned the formula to integrate this function today. Okay, so the integral of this one would be secant x tan x plus the integral of secant x is ln secant x plus tan x. You need to have the absolute value, of course, plus a constant. Okay. Now we are not done yet. Remember, we wanted to find I, but we have found 2i. How do you find I? Divide both sides by 2. That will give you I. So your I will be equal to secant x tan x plus ln absolute value of secant x plus tan x divided by 2 plus a constant c. Okay, of course you have the constant divided by 2, but when you divide the constant by 2, again you get a constant. I will put c itself without loss of generator. Okay, so this is the integral of secant cube x. All right, let's move on to our next example, the last example. This is the last example that I want to go over. All right, let's work on part A. We need to find this integral. Here we have not seen any specific rule to integrate a function like this. Here the key is to simplify this using some trigonometric identities. Okay, so what I'm going to do is before I start my integration, I'm going to simplify my tan 5x. Okay, I can write this as tan 3x times secant squared x minus 1. Notice that secant squared x minus 1 is tan squared x. Okay, so you have tan squared x times tan 3x, which is tan 5x. Now, if you distribute this, you get tan 3x secant 2x minus tan 3x. Now, this should be something familiar to you. Okay, we can use our table that we discussed at the beginning of this lecture to find a suitable substitution for this integral, the integration of this function. Okay, and then here this looks still a little different. That's something that we have not seen, but again we can do a small modification for this one. Okay, so what I'm going to do is I leave tan cube x secant squared x as it is, and then minus I'm going to write this as tan x times tan squared x. Okay, but we know that tan squared x, I'm going to write this as tan x times tan squared x, but tan squared x is secant squared x minus 1. Again, I'm going to put secant squared x minus 1 here, like in the previous case. Okay, now if you simplify this further, you get tan cube x secant squared x. Yeah, I guess minus tan x secant squared x plus tan x. Now I can start with my integration. My integration will become integration tan 5x dx, which is the same thing as integration tan cube x secant squared x dx. I'm just plugging this expression this expression for my tan 5x, okay, because tan 5x is equal to this. All right, plus, actually it should be a minus, the second integral, minus integration tan x secant squared x dx, plus finally integration tan x dx. Okay, so all what we need to do is we need to solve this integral. We know how to solve these two integrals from our table that we discussed at the beginning, right? So what you do is to solve these two integrals, let's go to the table and find the correct substitution. Notice that the powers of secant is even in both integrals. So let's go ahead and find the correct substitution from the table. So it looks like m is even. This is the correct substitution because m is the power of secant, which is even. In that case, the substitution is going to be u tan x. So the substitution for both integrals is going to be u tan x. So let's use that substitution. By the way, here I'm not going to show the details. All right, for these two integrals, you use the substitution u is equal to tan x. Okay, and then if you use that substitution, you will see that this integration and this integration becomes respectively these expressions. Okay, you have u cube du minus, pull it down a little bit, minus integration u squared du. Finally, I need to have the integral of this one. This is an integral that you know how to find this integral. Okay, so this is going to be plus ln cosine x, absolute value of cosine x. The integral of tan x is absolute value of cosine x. So basically what you do there is tan x is sine x divided by cosine x. You use the u substitution, u is equal to cosine x. That will show that this integral will be this one. All right, now if you find the first two integrals, you get u to the power 4 divided by 4 minus u3 divided by 3 plus ln absolute value of cosine x plus c. Okay, now I can back substitute for u. U is equal to tan x for these two integrals. So if I substitute tan x here, you get tan 4x divided by 4 minus 1/3 times tan 3x plus ln absolute value of cosine x plus c. That's your final answer. Okay. All right, let's move on to the next part. It is the next part. Again, we use some strategies to solve this integral. What I'm going to do is, notice that I already know the integral of secant cube x, right? Looks like I can get a secant cube x from this expression, because you have tan squared here. You can replace this tan squared by secant squared x minus 1. That's what I'm going to do first. Integration secant x times secant squared x minus 1 dx. If you expand this, integration secant x dx minus integration, pardon me, here secant cube x minus integration secant x dx. Now, as you can see, you know both of these integrals. You know this second integral by the formula that we learned today. You know this integral by the previous example, not the previous one before that. Okay, we found the integral of secant cube x, which is equal to this function. I can plug in that there. Okay, that's what I'm going to do here. Okay, so this will be equal to This is the integration of secant cube x from the previous example. This integral is equal to this expression right here, minus the integration of secant x is known by the theorem that we learned today. That's going to be ln absolute value of, maybe I will go to the next line, minus ln absolute value of secant x plus tan x plus c. Okay, that, and of course, if you want, you can simplify this a little bit, because you have ln secant x plus tan x. Here also ln secant x plus tan x, but here with the 1/2, you can simplify that. But this is going to be the integral. Okay, integration of the given function. All right, with that, we conclude section 5.4. I'll stop there. I'll see you next time.